Okay, so good evening, students. This is Dr. Zhong. Because of this holiday, the Labor Day holiday, so we are not going to have a class today. But instead, I'm going to stay at home and take this record this video lecture for you to study remotely. So today again, we're still going to focus on sorting algorithms, but today we're going to learn the second sorting algorithm called merge sort. So let's first do a quick review of what we learned from last week. So last week our main topic is insertion sort, and so if you remember, we went through the pseudocode of insertion sort. So and which recall what is the pseudocode. We have insertion sort A, where A is an array, and also we said that in our textbook and also in our lecture, to be consistent or to be general. So we followed the convention where the index of the array does not start from 0. Actually, it starts from 1. So we have this one for J starting from 2 to a dot length, where a dot length denotes the length of the array. And then first we have key. So key equal to aj, and then we have I equal to j minus 1, and then we have a while loop. Okay, so while I is larger than 0 and ai is larger than key, we have ai plus 1 equal to ai, and then we have I minus minus. At last we have, after the while loop, we have ai plus 1 equal to key. Okay, so this is the pseudocode of insertion sort. We said that the design of the insertion sort is inspired by the poker game. So in which we get so in the poker game we need to get cards from the table and make sure that they are in sorted order at our hands, so that when we play a card, we know which one do we want to take out in a very fast way. Okay, so the let's say currently we have maybe 4, maybe 5, whatever number of cards at hand that have already been sorted, and then we get a new card from the table. So now we need to insert the new card into the appropriate place at our hand to make sure that all the cards are sorted. So what we do is that first we compare the new card with the last card at our hand, which is the largest one, and then if the last card is larger than the new card, we move the larger card one place to the right to leave some space. Okay, and then otherwise we just insert the new card at the end of our hand, and then next time we just we just do this just do these iterations from the last card to the first card until we find a card that is smaller than the new card, and then we stop. So and then we insert the new card after the first card that is smaller than the new card. So this is the process for us to do the insertion sort, or maybe or similar, just doing the insertion by inserting poker cards. Okay, so we repeat this processes so that we make sure after we got all the cards from the table, all the cards at our hand are sorted. So and also last time we talked about some conventions in pseudocode, like say for example we say that pseudocode is the intermediate language between human language like English and actual code. So it is more expressive than the actual code, meaning that to express the same amount of information, it is much shorter than the actual code, maybe Java, maybe C++. But it is more formal than what I just talked before, than the human language. So after we say this piece of code, pseudocode, everybody can know, okay, this is a for loop and this is a while loop. And as I said in the last lecture, my task is to explain you, okay, why the pseudocode works. And then your task is just to, in your homeworks, your task is to translate this pseudocode into Java, okay? So very straightforward, okay? And then we also talked about a little bit about the complexity analysis. We say that we use complexity to denote, to kind of like describe how fast is the algorithm. And we have this for insertion sort. We have big O notation. We have big O n square complexity. Here n denotes the length of the array, the size of the input. Here because we're dealing with an array, the length of the array. Okay, so this is so it's not very difficult to understand that, okay, if we have a longer array, it may take longer time for us to sort, right? So yes, definitely with the growth in the length, we expect the growth in the execution time. But n squared just denotes, okay, it denotes how fast does the execution time increase with the length of the array. So for example, okay, so this is the execution. We have the y-axis as the execution time and x-axis as the length of the array. So if we have an algorithm that is O(n) complexity, meaning that the execution time grows linearly with the size of the array, okay? So then we probably can plot such a line, but because the complexity of insertion sort is O(n) squared, so if we measure the execution time against the different lengths of arrays, so most likely we are going to get a line like this. This is O(n) squared insertion sort. Okay, so here we basically use the big O notation to denote the worst case running time, execution time of an algorithm. By worst case, we mean that, okay, so because, say for example, if we want to sort an array whose length is 100, so if you give it an array that is totally empty, that it has already been sorted, then it's going to be really fast. So let's say, for example, to sort an array whose length is 100, it may take any time from 1 second. So this is the best case. Or in the worst case, if you just pass in an array whose length is 100, but which is inversely sorted, then it may take a lot of time for the algorithm to sort it. Let's say, for example, 200 seconds. So to sort an array of the same length, the execution time may vary from 1 second to 200 seconds. So by convention, we only report the worst case time scenario. So to give people a bottom line. So then we basically use the big O notation. Basically describes the worst case. Okay, in the worst case, how fast does the execution time grow with respect to the size of the array? Okay, so here we say that the execution time may grow quadratically with regard to the size of the array. And this is what we learned from last week. So before I step into our lectures today, I want to discuss some feedbacks that I got from you. So the first feedback number 1 is that, so immediately after last Tuesday, immediately after I upload the video lecture to YouTube, so I received, I don't know how many, maybe 3, maybe 4 emails from students saying that the video lecture is not clear enough. So they can't see the slides or my writings on the whiteboard clearly. So the first feedback is that the video is not clear. Okay, I think on Tuesday I also sent an announcement on Canvas saying that, okay, so because there are so our classroom is like this. In the front, this is the whiteboard, and then we have 4 lights in the first row. 4 lights in the first row. unfortunately, the middle two did not work at the time when I taught the first class in the classroom. So which makes the front of the classroom look very dark. Even the students who sit over here or over here, I think they don't see I don't think they can see the board clearly. Okay. And the other issue is that we have the video camera or the web camera installed at the back of this classroom. So unfortunately, this video camera is only comes with 720p, and it is not 1080p. So which means that it is not high definition video, and that's another reason why you didn't see it clearly. So here I'm thinking about, so I'm just giving you two options. The first option is that, okay, still I take the video, I record the video at the classroom because it includes some interactions between me and the students. But the next time when I took the video, I'm just going to say zoom the web camera more into the front of the classroom. So possibly you can see the whiteboard is going to be bigger in your screen, and also hopefully these two lights should be fixed by the time that by next Monday. So this is one solution. Okay, so the solution A is that we still stick to the classroom, we still give it a try. So the second one is that I'm going to say use this video lecture as an experiment. So here, the other option is that I record the video at home with this big iPad Pro and also with the Apple Pencil, so that you can see my writings on the screen clearly, even though I don't write clearly. I apologize for my writing. Okay. So this is the second option. Okay, and in the second option is that I'm so sorry. In the second option, so there is basically no direct interaction between me and any student, of course, because I'm sitting at home. But it is going to be definitely more clear. And please let me know which option do you prefer, A or B. Okay, so the other feedback that I heard from the students are that, so which IDE should they go for? As I mentioned in the last class, in the last lecture, or also in the video lecture, what I said is that I don't require you to use any IDE, but personally I recommend Eclipse because it provides very useful debugging tools, and also I'm pretty familiar with this IDE. I have been using it for more than, let me see, how many years? Probably 13 years. Yeah, 12 years, either 12 or 13 years. Okay, so I think it's a very good IDE, but some people may like JGrasp, so I seldomly use this one because this one is very basic. It does not come with very strong debugging utilities. So personally, I don't recommend you to use it, but if you are good at it, or if you want to stick to it, feel free. And also there are some other options. So the options include Xcode, and I think this is also very powerful, but I don't have a lot of experience with it. The other one is IntelliJ. This one is extremely powerful. So IntelliJ. Okay, so if you want to give it a try, feel free, and it should be more powerful than Eclipse. Okay, so again, I don't enforce you to use any. And also the third feedback that I received from the students are that I think two students sent me an email saying that they don't have any experience with Java programming because they're transfer students from the other colleges. So my personal suggestion is that either you spend a lot of time just going through Java materials, because again, as I said in the first lecture, this class is going to have a lot, very heavy programming assignments there in Java. So if you are not good at Java, it's going to be really difficult for you. So either be prepared to devote a lot of time to this class. I would say at least 10 hours per week, or especially in the beginning, okay? Or just go back, so withdraw this class and then take CSIT 111 and 112, which gives you more Java foundations. So I'm going to, so I don't want to enforce you to do anything, but this is my suggestion. I just want you to be successful. I don't want you to spend just a semester with us and end up with a score which cannot let you proceed to the next level of classes, or even worse, just let's say you just get a C or C minus grade, but you still cannot program efficiently in Java. Then when you go to the 300 level classes, it's going to be even more difficult for you. Okay, so these are the feedbacks that I've heard so far, and so for today our main topic is the second sorting algorithm named merge sort. So, and also we are going to do some complexity analysis over it. So in the first lecture, when we learned insertion sort, we basically solved the algorithm, solved the problem incrementally. So the idea is that initially we want to get the first two elements of the array, first two numbers in the array sorted, and then next time when we insert a new card or a new number, we want to make, after we insert a new card or new number, we want to make these first three numbers sorted, and then the first four numbers, 5 numbers, etc., etc. So here you can see that we basically solve the problem incrementally. In the beginning, so in the first iteration, we get the first two numbers sorted, and in the next iteration, we got the first three numbers sorted, etc., etc. So it's like we solve the problem incrementally. This is what we did in insertion sort. But today in merge sort, we are going to solve the problem from a different perspective, named divide and conquer. And divide and conquer is a very, very important, design philosophy behind for complicated problems. So let me give you an example of what is divide and conquer. Suppose today you received a phone call from your grandma saying that okay, she has a junk car which cannot be started or moved at her backyard. She wants you to help her to move this car from her backyard to a garage, or to another junkyard. Okay, so you need to move it to some place. So since this car cannot, and also your grandma saying that I'm not going to give you any money for it, so you have to do it with your hand. You cannot just rent a truck to move it. So obviously, if you want to push this car to that yard, maybe two miles away, it's going to be too much for you. Okay, and so what you can do is this. Okay, you can just disassemble the car to get the wheels, and then to get the steering wheels, and then to get the, maybe, I don't know, the next time should be the engine and also the seats. Okay, so you basically break this big car into small pieces, and each time you just use your hand to move one piece to the place, and to move the other piece to that place. After you move every piece to the place, to the destination, you assemble them into the original car. So then the next step is that you assemble them to the original car, so that you successfully finish the task assigned by your grandma, right? So this is how you solve a very big problem or complicated problem in real life. And so similarly, the in merge sort we follow the same philosophy, and the philosophy is called divide and conquer. In computer science we call it divide and conquer. So in divide and conquer we solve problems in 3 steps. Divide. So divide means that we break the problem, a big problem into small pieces, okay? And then conquer means that we solve each piece, we resolve each piece so individually, and then solve individually, okay? Solve the individual pieces. And then in the combine step, we combine the solutions of these individual pieces together, okay? So then we got the solution to the whole problem, to the whole big problem. So it should be easy to follow, right? Okay, so this is called divide and conquer, and it's just a philosophy or design pattern based on for multiple algorithms. So the most famous application of divide and conquer in computer science is just the merge sort algorithm, okay? So in merge sort algorithm, suppose here we get a very long array to sort. Okay, when you look at the array, you may think, okay, this array is too big. So here just divide it into half. Oh, let me make the problem easier. So sorry, let me just make it a little bit easier to have 8 numbers rather than 9. 1, 2, 3, 4, 5, 6, 7, 8. Okay, now I got 8 numbers. So here, suppose that you have an array with 8 numbers, and you think, okay, it's very hard for you to sort 8 numbers. So then you say, okay, I'm going to divide this big problem into 2 smaller pieces, each with 4 numbers. Okay, and then again you say this is again very difficult. So you keep dividing it. Then you divide it in this manner. Okay, you got 4 subarrays, each with two numbers only, and then you keep dividing. So here you got 8 subarrays. Each of them only has a single number in it. So let me ask you a question. If you only have a single number in an array, is that array sorted naturally? The answer is what? Is yes, because if you have an array which only contains one single number, there is no comparison, so it must have been sorted. So here, basically, this is the divide step. And then in the conquer step, it's pure. In the conquer step of merge sort, it's extremely easy. We just do nothing. Okay, there is nothing for us to do. We still got the same 8. So here we just divide a big array into 8 small arrays, where each of them just is sorted. So in the conquer step, we do nothing, but instead we do most of the work in the combine step. So in the first one, we just combine the first 2 numbers in the correct order so that the first 2 numbers are sorted, and then we combine the third and fourth number into a small array with 2 numbers, and also we guarantee that these 2 numbers are sorted. So then we combine them so that we got 4 small subarrays that are sorted, and then we further combine them 2 by 2. Okay, so then we got so in the left we got a subarray with 4 numbers that are sorted, and in the right subarray we got 4 numbers that are sorted. And finally, we combine these two arrays together, and then finally we get the array with 8 numbers sorted. So this is the combine step. Okay, as you can see that in the combine step we do most of the work, and and next I'm going to so again let's repeat the procedure. Okay, so in merge sort we have divide and conquer and combine. In divide we keep dividing the array until the array only includes a single number, and then in the conquer step we do nothing. In the combine step we keep combining the neighbor arrays neighbor arrays which have already been sorted into a sorted array, bigger but sorted array, until we got all the numbers combined. Okay, so this is the procedure of merge sort. And then let's look at the pseudocode. So this is the pseudocode for merge. Merge, it has another name called combine. Okay, so this is the pseudocode for the combine step. And then I'm going to discuss the pseudocode of the divide step later. So here, if we look at the parameters, we got 4 parameters, input parameters, which are capital A, P, Q, R. Obviously, A should be the array to be sorted, right? And what about P, Q, R? So the PQR, it's very hard for you to guess what do they stand for, but let me give you an explanation. So suppose that we have an array A, which is very, very long, and here I'm just saying, okay, I want you to combine these 2 neighboring subarrays which have already been sorted. So these 2 subarrays have already been sorted. I want you to combine them. So if I want you to combine them, at least I need to let you know, okay, where do they start and where do they end. So P is the index of the first element of the left array to be combined, and R is the index of the last element in the first array to be combined. Okay, and then this is Q, not R. I'm sorry. This is Q. Q is the any index of the first array, where and R is the any index of the second array to be combined. Okay, so we got 2 arrays to be combined. So now you may ask, what is the starting index of the second array? So this is the first, this is the second array, and this is the first array. Okay, so because these two subarrays to be combined must be neighboring each other, so the first index of the second array to be combined should be Q plus 1. Okay, so these are their index, and basically with PQR we are able to locate which fraction of the array do we want to combine. And then let's read the pseudocode more. First we have n1 equal to Q minus P plus 1, and n2 equals to R minus Q, and then we create 2 new arrays, L and R. The length of L is what? So think about what is the length of L and R respectively, and then we have 2 for loops, and then we got this. Okay, so L n minus 1, L n1 plus 1 equal to this operator. So what does this operator mean? This operator in math, it means, so if you have taken linear algebra or discrete math, or even also algebra. So if you have taken any of the 3 courses, which you should have already taken, right? So you should know that this means what? Infinity. Okay, infinity is an infinity large number. So this is the maximum number that you can imagine, right? So in Java, how do you represent infinity? So there is a constant named this integer dot max value. Okay, so this is the maximum value that an integer can have. So when you are doing your homework 2, you can just replace this infinity with this constant value provided by Java. Okay, integer dot max value, and then we assign infinity again to R n2 plus 1. And then we have I equal to 1, j equal to 1. We have 4 case starting from P to R, if and else. Okay, so what does this piece of code do? Let's use an example to go through it. Okay, so let me see here. I'm going to add here. I'm just going to add a page. Okay, so I'm going to write down the pseudocode on the left. We have merge A, P, Q, R, and then we have N1 equal to Q minus P plus 1, and then we have N2 equals to R minus Q, and then we let L N1 plus 1 and R N2 plus 1 be two new arrays. And then we have, so for I starting from, say, double check, I starting from 1 to N1, and we have L I equal to A P plus I minus 1. And then for J starting from 1 to N2, we have Rj equal to A Q plus J. Okay, so this is the first part of the pseudocode. I'm going to just focus on, okay, sorry, and also I forgot the other thing, that is, so we have L and 1 plus 1 equal to infinity, and we have R and 1 plus 1 equal to infinity. So this is the first part of the pseudocode. I'm just going to, again, I'm going to use divide and conquer in my lecture because the pseudocode is too long and I want to divide into two smaller pieces to discuss. So for now, let's just focus on the first part of the pseudocode. And again, I'm going to use an example. So the example is what I have showed above. So we have an array A, so which is very long, and a fraction of it is 2, 4, 5, 7, and 1, 2, 3, 6. So the index or okay, so these are the index of the array, and this is the actual array that we have. So here, for now, let's say we call the merge function on this array, and then so if you look at here, we have two small arrays that have already been sorted. They are, let me use a different color. Nope. Let me use a different color, maybe red. Okay. So we have two small arrays that have already been sorted. The left subarray is 2, 4, 5, 7, and the right one is 1, 2, 3, 6. So we want to use the merge function to get these two small subarrays combined and to make sure that after the combination, these 8 numbers are sorted. Okay, so as what we discussed before, P stands for the starting index of the left array. Q stands for the end index of the left array, while R stands for the end index of the right array. So here we have P equal to 9 and Q equal to 12 and R equal to 16, right? So let me write down use a different color. So let me write down the variable numbers. So when we pass in the values, we have P equal to 9 and Q equal to 12 and R equal to 16. Okay, so so next let's do the let's follow the pseudocode to go. Let's follow the pseudocode. So let's assume that we pass in the parameters with A, P, Q, R, and then we want to execute the following code. So first we have N1 equal to Q minus P plus 1. So if we do the numbers, Q is 12 and p is 9 plus 1 is, so this will be 4. So do you know what does this stand for? What does n1 stand for? n1 stands for this, and n1 stands for the length of left array. Okay, so it basically calculates how many values it calculates that how many values are there in the left array. We use the end index minus the starting index plus 1. Okay, so let me put it in another way. How many days are there in 1 week? 7, right? Everybody knows it. So, but how do we get 7? The first day is Monday, 1. And what is the last day? Sunday, 7. So we use 7 minus 1 plus 1. We use the ending minus the beginning plus 1. That is 7 minus 1 plus 1. 7 days, the length of a week, right? So similarly, this is what we do over here. And then guess what's the value of n2 over here? So it is 16 minus 12. It is 4. Yes. So n2 should stands for the length of the right array. Okay, the length of the right array. So we just use the, because for the right array the ending index is r, the beginning index is what? Is q plus 1, and then we plus 1. So in total it is q r minus q. Okay, so here we basically calculate the length of the left and right array. Let's also mark the variable values over here. We have n1 equal to 4 and n2 equal to 4. Okay, so then we create two arrays, L and R. So their length is n1 plus 1 and n2 plus 1, because n1 and n2 are both 4. So the length of L and R are going to be 5 each. So then we just create two new arrays whose length are this. Okay, we're just going to create two new arrays whose lengths are, this is L, this is R. So let me make it look better. We have this L, over here R. Okay, so this is L, this is R. Each of them has 5 spaces, and for I starting from 1 to n1. So what is the value of n1? It is, if we go to this variable table over here, you probably can know that the value of n1 is 4. So for I starting from 1 to n1 to 4. Okay, so we, in the first round we have I equal to 1, and so as I told you last time, okay, by convention we use I and j as the index of the array. So here we use them as the index for left, I as the index for L, and j as the index of R. So let me mark the index of them first. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so because we are going to use I as the index of L over here, from here you can see that we're going to use I as the index of the array L. So for initially we have I equal to 1, so we're going to mark I over here. Okay, so in the first round we have L1. So let's figure out what's the right value. The p value, the value of p is 9, and the value of I is 1 minus 1. So 9 plus 1 minus 1 is what? Is 9. So if we want to make it clear, we can say this sentence is basically saying that we're going to assign is this. Okay, we're going to assign A9 to L1. So A9 is right over here. So we're going to copy the value from, so let me remove this. Okay, we're going to copy the value from here to here, right? We're going to copy it from A9 to L1. So this is L1. So here we do a value copy. So we got 2 over here. And in the next iteration, so next we're going to go to enter the next iteration, and then we are going to increase I by 1. We have I equal to 2. So then this sentence is going to be L2 equal to, so let's say what's the value, okay? And so we have the left as L2, and then we have the right as P is 9, plus I is 2, minus 1 is this. So in total, sorry, so delete. So in total, it will be, this will be a 10. Okay, so we are going to assign a 10 to L2. So we're basically going to copy the value from a 10 to L2. And then the value will be, the new value that we put in the L is going to be 4. And the next, we're going to increase I by 1, sorry. Increase I by 1. And we have I equal to 3. And here we should change the I to point to here, okay. We have I over here, okay. So and then so if we do some calculation, it should be okay. It should tell us that on the right we have P is 9, I is 3, minus 1 is, so it will be, A11. So we're going to assign A11 to L3. So we're going to do this. So basically here, after 3 iterations, you can tell that we basically copy everything from the left array to L. And then in the next one, we increase I by 1, so the new value of I is going to be 4. And then so we have this equal to what? This can be rewritten as L4 equal to a 9 plus 4 minus 1, which is a 12. So we're basically assigning a 12 to L4. A12 is here. Oh, sorry, I forgot to move I to its correct place. Okay, so then we copy the value. And then we have L4 as 7, okay? And here we just, and then the first for loop terminates because I already reaches its maximum value, which is 4. So here we can, if we want to summarize what we do over here, we basically copy left array to L. Okay, and then the last place of L is left blank with no value in it. So next, let's say what does the next for loop do? So probably you can guess, right? So you should do similar thing as before. So initially we have j starting from 1 to n2. n2 is 4, so the maximum value that j can have is also 4. And then the initial value of j is just 1. Okay, so initially we have j equal to 1, and we are going to use j as the index of the array R. Initially we have, so in the first iteration we have R, sorry, let me use a different color. We have this, we have R1 equal to a q plus j. The value of q is 12 and j is 1. So we are basically assigning a 13. We're basically assigning a 13 to R1. So A13 is right over here, and we're assigning to R1. So here we copy the value from A13 to R1. So the first value of R is 1. And then the second value, so in the next iteration, we're going to increase J by 1. So the new value of J is 2. So J is going to point here. And then it should be rewritten as this, okay? So actually here, we don't need to do it step by step. It's not hard for us to tell that. So we have Q fixed. Here we have Q fixed. Q is fixed. So what only changes is the value of R. So sorry, the value of J. So here, or in the last loop, we have R1 equal to A13. So in the next loop, we're going to increase the index of both the left and the right hand side by 1. So we have R2 equal to A14. And then we are going to copy the value from A14 to R2. So the new value here will be 2. And then in the next one, it will be after we increase the value of J to 3, and then we move J right over here. Then this statement, the statement should be R3 equal to A15. So here we just copy the value. So, and in the last iteration, we'll just copy the last value of the right array to R. So we got, so here in the second for loop, we basically copy right array to R, and then we need to execute the last two statements, so which are this, because n1 is 4, so this statement could be rewritten as L4 plus 1 which is 5, L5 equal to infinity. So we are going to assign infinity to L5, and then we're going to assign, similarly, this will be R5 equal to infinity, because, sorry, the pseudocode is a little bit wrong. This should not be N2, it should not be N1, instead it should be N2, because N2 is also 4, so it will be R4 equal to infinity. And here we just assign infinity to R. Okay, so this is what we end up with the first half of the merge algorithm. And then next, let's go to the second part of the for loop, okay, of the algorithm. Let me get rid of everything. So I'm going to write the second part of I equal to 1, J equal to 1, and for K starting from P to R, if Li is less than or equal to Rj, we have AK equal to Li, and I++, else we have AK to Rj and J++. Okay, so this is the second part of the pseudocode. It's relatively simple compared with the first half. So let me get rid of the values that we got. So here, okay. So it looks cleaner. So the value of P is 9. So, and So in the first two lines, we basically assign new value to I and j. So here we are going to remove so we're going to assign new value to I and j with both of which are 1. So this will be delete. Okay. So again, we're going to use I and j as the index of the array L and R. So we have I and j in the beginning of the array, because both of them have value 1. Okay, so for k starting from p to r. So what is the value of p? So if we go to the table, we can find, okay, the p is 9 and r is 12. So here we're just going to create a new variable whose initial value is r is not 12. R is 16. So the value of k should start from 9 to 16. And if you look at the table that we have, the array we have, A over here, okay, so basically k is going to start from p and end up with r. So here it's not too hard to tell that we are going to use k as the index of the array. So initially index of the array A, initially k is the same as p, whose value is 9. So it points to the first place of the left array. Okay, so here we're just doing, and next, if Li is less than or equal to Rj, so what is Li? Here we have I equal to 1. So if we have I equal to 1, then Li is going to be 2. And here we have j equal to 1. So Rj is also Rj is 1. So here we're just comparing 2 versus 1, and it's easy to tell this statement is false. So we're going to go to the else. We're going to execute the statements in else, and then we have ak equal to Rj. We're going to copy the value from R1 to AK to this place. So we're basically going to assign the value from Rj to AK. So the new value that we're going to assign over here is 1. Okay, because it is from Rj. And next we're going to increase j by 1. So the new value of j is going to be 2. Okay, so the new value of j is 2. So we move j to this place. Okay, so from this, so here j points to this place, and also I'm going to mark this place as x, or kind of like eliminate it, because yes, this value has been copied to the array A. So here, let me ask you a question before I proceed. So suppose that we have 2 groups of students in the classroom, left and right, and so suppose that I know that the students in both groups are sorted by the GPA from the highest to the lowest. So the students with the highest GPA in the left is the first one. So this person has the highest GPA from left, and then this person has the highest GPA from the right. If my task is to find the person with the highest GPA in the whole classroom, what I'm going to do to make the task simple? So I should only compare the GPA of the 2 guys in the front, and which one has higher GPA should be the guy with the best GPA in the classroom, right? This is pretty simple, right? So on the right we have the same logic in the algorithm. So if we want to get the subarray with 8 numbers sorted, then who should go to the first place? What value should go to the first place? Let me use a different color. What kind of value should go over here? The smallest among the 8, right? So here, because we have this left and right array sorted, so here we're just comparing their first values to get the first value of L and the first value of R to see which to get the smallest value from the 8 and assign it to the first place of A. So this is the same as what I said before. The reason now, after the first iteration, we increase J by 1, so J has the value 2, because this is kind of like this student has already been removed from the classroom, then also from the right hand side of the classroom. Then in the remaining students of the right side of the classroom, the guy has the highest GPA is this guy. So we're going to compare this guy with the guy at the left to see which one has higher GPA, or in our case has the smaller value. Okay, so so in the next iteration we're going to increase J by so here we just increase J by 1. J has the value 2, and then we go back to the for loop, increase K by 1. So the new value of K is going to be 10. So we move K right over here, and then we're comparing Li with our J. So here we have Li equal to 2, but for our J it has a new value, it is also 2. So here it is also 2, and this statement is going to be true, not false. So we're going to execute the two statements in the if. So we are going to execute Li equal to AK. So we're going to assign Li to AK, and so then the new value of this place is going to be 2. And then we're going to increase I by 1 according to this line. We're going to increase I by 1. So the new value of I is going to be 2. Okay, and the reason for us to do that is because this value is gone, and then the smallest value at the left is just right over here. So in the next round we're going to compare these two values. So in the next iteration we increase K by 1, so K is going to be 11. We move K right over here, and then so we're comparing Li versus Rj. So we have Li as 4 and Rj as 2. So obviously it's false. So we're going to execute the else statement we have. So we are going to copy Rj to AK. So the new value of this place is going to be 3. It's going to be 2. And then we're going to increase J by 1. So the new value of J is 3. J goes here, and this value is gone. Has gone to the array A. Okay, so then in the next iteration we're going to increase K by 1. So K is going to be 12. We have K over here, and then so we're going to compare. Next we're going to compare Li versus Rj. So we have Li equal to 4 and Rj equal to 3. Rj is right over here, and Li is right over here. So obviously this is also a false, so we're going to execute the two statements in the else. So then we are going to assign Rj to AK. Okay, so the new value in this place is going to be 3. And then we are going to increase J by 1. J is 4. And then so the new value of J is going to be 4, and then we're going to cross out the value that has already gone to the array A, and then so we go back to the for loop, increase k by 1. So the new value of k is going to be 13. So we're going to move k right over here. Okay, so and then we're going to compare Li versus Rj. The Rj is 6. Here we have Rj as 6, so this is going to be true. We're going to execute the two statements in if, and we are going to assign Li to ak. So we're going to assign it this. So the new value of ak is going to be 4, and then we're going to increase I by 1. So I goes, the new value of I is 3, so I goes here, and then so we go back to the for loop, we increase k by 1, so the new value of k is 14. And then we compare Li versus Rj. Rj is not changed, while Li becomes 5. So this is true again. So we're going to copy Li to ak. Okay, so the new value of ak is 5. And then we increase I by 1. Oops, sorry. Increase I by 1. So the new value of I is going to be 4. And then we go back to the for loop, we increase k by 1. The new value of k is going to be 15. So k goes here. And then we're going to compare Li versus Rj, and here we have Li as 7. Okay, so this is false, and then we're going to assign Rj to ak. And then so the new value of ak becomes 6. And then we're going to increase j by 1, so the new value of j becomes 5. Okay, so j goes here, and this value is gone. Okay, and then in the next one, we're going to increase k by 1, so k goes to 16. K goes to 16. And then we're comparing Li with Rj. So Li remains the same, which is 7, and Rj is infinity. Here you probably can see why should we append an infinity to the end of both the left array and the right array. The reason is to guarantee that it's the original value to be copied. It's the largest value of the original 8 values to be copied into the array A, rather than the new appended value. If we assign 1000 or 2000, if the largest value in the array, for example, is 3000, then it is the appended value that goes to the end of the array, right? So here. And then here we're just obviously the if statement evaluation is true, so we're going to copy Li to ak. So then the value becomes 7. Okay, and then we increase I by 1, but this is not important at all. So then so some of you may say, okay, we should go back to the for loop. No, the reason is because k already reaches its largest value, 16. So we can't. So we reach the end of the for loop and also the end of the algorithm. At the end of the algorithm, we see that, okay, now we got an array with 8 numbers sorted. Okay, starting from P to R, these 8 numbers have been sorted. 1, 2, 2, 3, 4, 5, 6, 7. Okay, in the beginning, okay, before we start that process, the 2 subarrays we have are 2, 4, 5, 7 and 1, 2, 3, 6. So this is how we got this 2 small sorted subarrays merged into a big sorted array. Okay, so hopefully that you understand this process. And so people have some mathematical proof to show at the end of the merge function, after the merge, all the numbers should be sorted. Okay, so and here we just finish that part, the combined part of the merge sort. And now I'm going to discuss the divide part of the merge sort. As you say previously, okay, in the divide part it's pretty simple. Given an array, we just keep dividing into 2 halves until the array only includes a single element. Okay, so here is the divide part. Okay, here is the divide part. In the divide part, we have the merge sort. We call the function merge sort. It takes 3 parameters, the array A, P, and R. So here, let's just, for another example, say again we have an array which is very long, and suppose here we want to focus on this part of the array and get it sorted. So P stands for the starting index, and R stands for the ending index. Okay, so and then what it does is that first it compares the starting index and end index. If P is less than R, we do something. Okay, so let me ask you one question. Okay, if P is the same as R, what does that stand for? It stands for that we are just P and R point to the same place. The subarray that we want to work on only has a single element. So if the subarray only includes one single element, there is no action that we need to do, right? So here it guarantees. So this condition makes sure that the array includes at least two elements. The subarray includes at least 2 elements, and then it calculates Q as so you may wonder, what does this mean? Okay, this means the floor. Okay, so suppose here we take the floor of 4.5. It is going to be 4. If we take the floor of 1000, it is going to be 1000. So here, giving any value, giving any float value, it just changes keeps the integer part of that value. Okay, so this is the operation of the floor. Okay, so here it calculates P, the average of P plus R, the average of P and R. In other words, it calculates the middle point. Okay, so Q points to the middle point. Okay, so here, so it basically calculates where is the middle of the array. So here next, so what it does is that, so it finds the middle point of the subarray and say, okay, I'm going to split it into 2 halves. This is the left and this is the right. This is the left and this is the right, and it is going to say I'm going to merge sort APQ. So it's like I'm going to sort this part, and then I'm going to sort that part, Q plus 1 and R. Q plus 1 is the starting index of the right array, and I'm going to sort this array, and finally I'm going to merge them together. Okay, so as previously what we said, the logic is that we divide it and then combine the divided, work on the individual pieces and then combine the solutions. This is exactly the same what we discussed before, right? So this is the pseudocode for the divide part. Okay, the last thing that I need to talk about is the complexity of the algorithm. The complexity of merge sort is O(n) log n. So you may wonder, okay, so previously we learned insertion sort, whose complexity is O(n) squared, and here we learn insertion sort. Okay, we learn merge sort, whose complexity is O(n) log n. So my question is, which one is faster among these 2 algorithms? So think about it. And if you're not sure about it, you probably can find after you finish your homework too. Okay, so okay, let me give you the answer. So basically we want the algorithm to be as fast as possible, so the complexity should be as lower as possible, right? So let me ask you one question. Which one is larger, log n or n? The answer is absolutely log n is smaller, n is larger. So we have this, okay? The complexity of merge sort is lower than insertion sort, which means that merge sort is more efficient. Okay, so if you want to see the detailed proof, actually, if you want to see the detailed proof of this complexity analysis, please refer to the chapter 2.3.2. And my suggestion is that if you consider doing a graduate study, especially if you want to do research or PhD, and I highly recommend you to read it. This is going to be what you do in research, purely math, and it's purely beautiful. And so after this class, so you must read chapter 2.3.1, and also you have your programming assignment, which is homework 2 on merge sort. Okay, so and besides merge sort, and there is one more thing I want to discuss, which is the heap sort. This is totally optional. Okay, so besides heap merge sort, there is another algorithm which can give you O n log n complexity. But this algorithm is more complicated, way more complicated. So if you are interested, please refer to the slides and chapter 6.1 to 6.4. Okay, this algorithm is really challenging for you to understand because it includes, let me say, 4 or 5 algorithms. Okay, 4 or 5 functions actually. So if you want to challenge yourself, or if you want to learn more about algorithms, feel free to do it by yourself. Okay, so thank you, students. Hope that you can have a wonderful week.